All right, this is the third in the series and our final one on control charts. It was the first video did X-bar charts and range charts because they fit together, therefore measuring things we can measure like weight, height, volume, those types of issues. Then we looked at P charts, which are percentage failure. So we look at number of observations in our sample and we look to see which ones pass and which ones fail. We count a percentage of how many fail. That's what goes into the P chart. Finally, though, we're going to look at C chart, which is the most rare, I would say, of control charts to use. And so, of course, it's the easiest to calculate. But let's give it a try anyhow. So we talked about that. We're going to be looking at things that we can count. So attributes, counting the occurrence of an event, a scratch, a misalignment, a missing part, an error on a document, those type of things. So we have 16 of them, 11 of them, 42 of them, 500 of them, those type of things. C charts, aka count charts, are used when measuring defects that we can count, covered that, but here's the difference. We still take a sample, but instead of averaging observations or calculating the percentage failure, we actually count the total number of failures in the sample. So a single unit could have multiple defects. So it's if we delivered a desk, then we'd inspect the desk and see, oh, there's a scratch over here. The leg's a little too short. There's a scratch over on this leg. So there could be 17 defects in this single unit. And then we go to the next unit in our sample and count how many defects are in it. And so it's a very different kind of situation, but it certainly can happen. It's something we can use. So we'll still use control charts to detect the pattern, but we need to calculate the UCL and LCL using another different equation. So still going to go with the chart. Here we go. Things that we count, got that. C charts, count them. Here's the formulas. The upper and lower control limit of C for a count chart is C. That is the expected number of defects in a sample. So again, like we've talked about before, we might go to the previous 20 samples and say, in those 20, how many defects, what was the average across those 20 samples? So again, it's like that grand mean, that X double bar that we had seen previously. So C can be estimated based on at least 20 previous samples. In the case of the problem we use, we're just going to use 5 because I don't want to have to add up 20 numbers, but you get the point. We see Z again. That's our same old Z that we always wrestle with. So Z, if it's for 95% confidence interval or a 5% chance of a type 1 error, it's going to be 1.96 or simplified into 2. And then it's the square root of C. It's that same C again. So let's give this a try. We'll go right to the problem. The school board is trying to evaluate a new math program introduced to second graders in 5 elementary schools across the country this year. A sample of the students' scores on the standardized math tests in each elementary school yielded the following rates. So we could expect, and it says in the column, that's the number of test errors in each sample. Now we don't know what the sample size is, but thankfully for a C chart, we don't need to know. The sample size always has to be the same. So we have 5 schools. School A had 52 errors, B had 27, C had 35, and so forth. I went ahead and calculated the average for you, so C is 42.6. Construct a C chart based on a 99.73 confidence. So right away, we know Z is going to be 3. What does the chart tell you about the results of the 5 schools? So let's calculate our upper and lower control limit. So our upper control limit is C, which we know is 42.6. It's not a percentage, so you don't have to do any decimal movement. It's just 42.6 plus Z, which is 3, times the square root of 42.6. Sorry, I've got a typo there. It's not the upper control limit again. It's the lower control limit, and I did correct the sign. It's C minus Z times the square root of C. And if we put these in, our upper control limit is 42.6, blah, 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 62.18. And our lower control limit is 23.02. So we get our control chart back out. We put our values in. Now in this case, we knew that the overall mean of the exam is 42.6, so we can put that in on the mean line. And I'm just curious, I want to take these 5 school samples that we have and plug them into the chart. Now this is a little contra to what we've looked at before, because these aren't time values where we can watch a pattern for them to go out of order. We're just trying to see if the schools fit within the control chart. So the pattern's not going to matter, but school A fits in. School B is looking okay. School C is very close to the mean. School D, a little higher than the mean, but everything's within the control limit. And then finally, school E also. So you got to be a little careful here, because our control charts have always been about samples over time. And in this case, it's not about time. It's about different schools. Now, there's other situations where if we're manufacturing tables or chairs or desks or cars, then time might be a factor. We might find that later in the day, employees get tired or machines overheat and they create more errors. So in that case, if we did our sampling across a day or a week, we might find that there is a time influence, and we would see a pattern in this data we would have to be conscious of. But in this case, it's not a time-based sample, it's just 5 different schools. So anyway, not too difficult to solve these, but it's a very unique case. So read the problem, and usually in the problem it'll give you a hint and say, this is a C chart. So just use this approach to it.